Okay, so the recording has started now. Now I'll share the screen. So I hope like you are able to see my screen.
Yes, sir. Yes, sir.
Okay,
Thank you.
okay. Yeah. Thanks for the confirmation. So hello everyone. This is NPTEL CS52 reinforcement learning course, and this is the week 8. And I'm Sandarbh from CS department IIT Bombay. And this meeting is done on 19th March 24. So as usual, like these are the details, like this meeting happens on Tuesday, 6 p.m. to 8 p.m. Same link. And anyone who has taken the course can attend. There will be discussion on practice assignment, then assignment, problem solving and doubt clarification. And this is to ensure that there is two-way communication. And the expectation as usual is that you should have watched the weekly lecture videos of like week 8 and at least made an honest attempt on weekly assignment and practice assignment. Also, it is highly recommended to read the Sutton and Barto reinforcement learning book. And these slides and recordings, as usual, will be available in the same Google Sheet. So keep yourself muted. And if you have doubts, you can unmute and ask or just ask in chat. And today, like there will be some problems which will require solving. So I'll be giving time for you guys to solve them simultaneously, and we will follow the usual order: first practice assignment, then problem solving. Like these problems are different from the problems in practice assignment and assignment, and in between there will be a demo. So today's demo will be on fitted queue equation, and finally we will move to assignment. So these are the like week 8 topics: function approximation. So here, like till week 7 we were like focusing on like tabular approaches. So we realize like if we have like large or continuous state spaces and action spaces, then it becomes infeasible to like store this big table in our memory. So we went for function approximation approaches. And in that, like we saw like one of them was linear parameterization is one of them. You can go for non-linear also. Like basically neural networks are non-linear. So this will come in lecture like week 9, where we will move to non-linear parameterization also, and one of them is neural network. And we saw state aggregation methods also, and function approximation and eligibility traces. And finally, we saw like these four approaches where least squares temporal difference and least square temporal difference using q values, and least squares policy iteration, and finally fitted q iteration. So let's begin with the practice assignment. So if there is any doubt till now in like last week topics, you can ask me. Otherwise, like I'll start with the practice assignment. So the first question says, assuming that we use tile coding state aggregation, which of the following is the correct update equation for replacing traces? Important word is like replacing traces for a tile edge when the indicator variable is 1. So indicator variable 1 means like we are visiting that state, right? When we are visiting that state, like what do we do generally in replacing traces? We set equals to 1, like the eligibility. So basically like this is for accumulating traces, right? So this is not correct. And this is like decaying, but like this happens when h equals to 0. Basically when we don't visit, then we are decaying it by gamma lambda. So this is also incorrect. And this is the correct one, right? In replacing traces. So we like make it 1 so that like it doesn't go beyond 1. So there is a maximum limit. It can eligibility can go till 1, and after that it will decay. When we visit, then again it goes to 1, then decays. And the fourth option says that replacing traces are not well defined. So this is also wrong. Using indicator functions, we can define that. So the next question says, this is regarding least square policy iteration. It says that it can be used for continuous action spaces. So like, yeah, like true, it can be used for continuous action spaces. In fact, this is one of the advantages of least square policy iteration, that it can be used for continuous action spaces. And the reason they have given is that we can use samples of state action pairs to train a regressor to approximate policy. So since we are dealing with continuous action spaces, we are using a regressor. If it was discrete, then we would have trained a classifier. So is this reason correct? Like we can use samples of state action pairs to to train a regressor to approximate the policy. Suppose like if our regressor is some kind of neural network, and suppose our coordinates are like state features are state variables x, y, z coordinate, and in between like there are some hidden layers who can connect them. So these connections are there. Suppose hidden layer, and then like we can have, and our goal is to like predict the velocity maybe. So this node can output something continuous. So in this way, like we can use a neural network regressor. Here it acts as a regressor because it's outputting a continuous value. So we can use a regressor because this will be our state and this will be our action. So it learns a mapping between that. So we have samples of state action. We can train a regressor to approximate the policy. And this is generally known as policy network. So this is also true. And the reason like it actually explains this why we can use this LSPI in continuous action spaces. So both assertion and vision are true, and the reason is correct explanation for assertion. So is there, if there is any doubt, you can ask me. Otherwise, I'll move to the next one. So this is like true and false. So for LSTD and LSTDQ methods, as we gather more samples, we can incrementally append data to the A and B matrices. Remember these matrices? So in class, we did derivation where A theta equals to B, and this allows us to solve and to stop and solve for the value of theta pi at any point in the sample trajectory. So if you remember correctly, like this value of A, like there was some 1 by L and summation, and in this also 1 by L and summation. And then like this 1 by L, like we can cancel it since it appears on both sides. Then this summation basically like it made it incremental. So we can do it incrementally and at I think any point we can stop and like compute solve for this theta pi, because this is matrices A and this B is changing like in an incremental manner. So at any point of time, we will have a snapshot of these two. And then we can take that snapshot and solve for this theta. So we can use some solvers for solving this. So this is also true, right? We can incrementally do this. Now, if there is any doubt, you can ask me. Otherwise, I'll move to the next question, which says, which of the following is the correct update equation for eligibility traces with linear function approximator? Okay, so this is the linear function approximator which they have given. So generally, like we were using theta till now. Here, like they have used W to represent the parameters. So you can map these. Right? So they're like we were using theta as parameters here. Just the notation is different slightly. So these issues you need to handle. Like sometimes W will be used. W stands for weights. So since like we are using linear regression kind of linear function approximator, so this will be weight of all the features. Like and then like we are doing this dot product between these two vectors. So the question is, which is the correct update equation for eligibility traces? So like basically like the equation for eligibility traces, like this is something very general, right? Is gamma lambda times eligibility trace minus 1 and plus we will have gradient, like there it used to be theta, we will have W here, and what is V of ST. So we need to take gradient of this quantity with respect to W. So you can see like this gradient is quite simple since it's linear. This will come out to be phi of ST only. So which is the correct option? Uh, Phi of ST, this one. ST minus 1 is wrong. W won't come because we are taking gradient with W only. And again, this will be wrong. So the correct option is option B. So this brings us to the end of section 1. So if there is any doubt in any of the question, you can ask me. Otherwise, I'll move to the next segment, which is problem solving. So the first problem says Is the problem of non-stationary targets an issue when using Monte Carlo return sets targets? So you remember like we were having this problem of non-stationary targets because like we were using, if suppose we were using some estimate, bootstrapped estimate, then essentially suppose some RT plus gamma times some value, then this was our estimate only. And if we were using some target, this as target, so this is also moving, and like this was not fixed, so it wasn't stationary. So, but in if we are using Monte Carlo returns as targets, in Monte Carlo, like we don't do bootstrapping, right? There is no bootstrapping in Monte Carlo. So what we do in Monte Carlo is we will have maybe t plus 1 plus gamma times t plus 2 plus gamma square times t plus 3, and we will carry on until the episode ends. So there is no bootstrapping here. So the targets are kind of stationary here. Like these won't change, right? Because we are not having some value function or q value function here, which will keep on incrementally changing. So since the targets are fixed, so here like Monte Carlo returns like don't face this issue. So is the problem of an issue? So in case of Monte Carlo returns and targets, this issue doesn't take place. So correct answer is no. I think there is something. Okay. Now I'll move to next question. So is a parameterized representation of the value function. In a parameterized representation of the value function, suppose we use a feature which acts as a counter of some concept in the environment. Okay, so number of this they have given as example. So you remember this robot example which used to collect cans, waste cans. Does such a feature used for representing the state space leads to a violation of the Markov property? So what was Markov property? Markov property was that history basically doesn't play a role. So suppose if we have a trajectory of states like this, so the probability of moving to state ST, given this history, suppose when this goes to S0, this is essentially equals to probability of ST upon ST minus 1. This is the Markov property. So basically like last state is sufficient for that. Now we are using a feature which is number of cans. So suppose initially the robot has one can, then maybe like at some step like it will get there might happen that at some time step it won't get an extra can, but next step it can get an extra can, then next step it can get, and in this way. So we basically don't need history here. So we can get the next state based on previous state itself. Suppose it had like two cans here. If it got a can, then we can simply increment it by plus 1. So we don't need to rely on history. So suppose at some point it was at 27 and it got a can. So it goes to 28. We don't need to know what happened before this 27. We can simply use this 27 to get to this. So this doesn't violate the Markov property because like we can simply use the last state to get the current state. And like this is just one of the features. There might be many such features, but this feature definitely does not violate the Markov property because we can simply use the last state to get the information about current state. So you can have some kind of rules. If like it collected a can, then 2 plus 1, otherwise keep the same value. So now the question is, which of the following will affect generalization when tile coding method is used? So modifying the number of tiles in each tiling. So you remember this tile coding. Suppose it was like this, and then so this is like one tiling, and it has like 9 tiles. So this entire thing is known as tiling, and it has 9 tiles. Then we can have like more than one tilings. Like suppose if it's like this, and we can have like this, and like another tiling is there. So these tilings, like now that number of tilings are 2. So if we modify the number of tiles in each tiling, will it like affect the generalization capability? So what happens like if we modify the number of tiles in each tiling? Basically, if we modify the number of tiles, now it will affect the range over which like one state can generalize to other. Suppose like these tiles will become small if we like modify the, suppose initially we had 9, now we move to 16 tilings. So these will become small. So the range will become small. So in that way, like these will affect the generalization. Modify the number of tilings. So if we increase the number of tilings, then those indicator functions will like kind of increase. So basically the indicator functions will be for our state will be equal to the number of tilings. So that will also affect the generalization capability, right? And modify the size of the tiles. So the C option is essentially equivalent to 1. If you modify the size of the tiles, it will essentially modify the number of tiles in each tiling. And modify the shape of tiles. Again, like you remember this example from class in which we were using some coarse coding this kind of. So obviously, it also affects the generalization because like now, like suppose an update comes, now it will go in this region. Initially, maybe if the shape was square, it was going in this region. So this also affects the generalization capability. So this was a multi-option correct. So all four options are correct here. If there is any doubt, you can ask me. Otherwise, I'll move to the next question. Okay, then I'll move to the next question. So for a particular MDP, suppose we use function approximation and using the gradient descent approach converge to the value function that is the global optimum. Is this value function the same in general as the true value function of the MDP? Suppose the true value function of the MDP is V phi, and we are using like some function approximation and we use then gradient descent to converge to a value function that is the global optimum. Suppose this is V cap of pi. So they are asking whether like in general these two are same. Like remember like when we did function approximation, we compromised on something. We compromised on this closeness, like it, generalization capability basically. So what happens is like if we were having tabular approaches, then we will be having one value exactly for each of the state. But now since we are using function approximation, so some of the information is getting lost here. So it might not be possible that it will reach, it will be exactly equal to this. It might get close, but in general, like we cannot say that it will be equal to the true value function of the MDP. So the correct answer here is no. It might happen that it might reach, but in general, you cannot say that this will happen all the time. Okay, then I'll move to the next one. So the next question says, which of the following methods would benefit from normalizing the magnitudes of the basis function? So basis functions are basically your phi's. Remember phi I of s, where I equals to 1 to k. So these are your basis functions. So initially, like we didn't put any restriction on them. Like they can take like any value, like the continuous value, they can take in 5 to -5 to 5 range, or like we didn't put any condition, right? They can take any value, these features. But the question they are asking, if suppose we normalize the magnitudes of these basis functions, suppose we restrict them that you can take values only in -1 to 1, and we like map these to this range. So which of the methods, following methods would benefit from such a normalization? So online gradient descent, linear gradient descent, LSPI. So the question they are asking is like some of these methods will benefit from normalizing. Definitely, like gradient descent with based methods benefit from normalization because like normalization helps in like maintaining things in a slightly bounded manner. So this helps in gradient descent methods. So definitely these two will benefit from that. But in LSPI, were we using gradient descent? No, we weren't using gradient descent, right? We were like solving a system of linear equation, and accordingly we were having like regressor or like classifier. And there are procedures in this domain which like are kind of resistant to this like scaling. So this won't benefit, and none of the again this is wrong. So again, this question was more of a knowledge question, like if you knew already about gradient descent that normalizing of the magnitudes helps it, then you could have answered it. So now the next question says, suppose that the individual features phi a SA used in the representation of the action value function are non-linear functions of S and A. Is it possible to use LSTDQ method in such scenarios? So what they are saying is like this phi is non-linear function of S and A. So remember one thing, when we say linear, it is linear in parameters, like this parameters theta, not in phi. Phi can be like non-linear. So this like is not just related to reinforcement learning, but in general machine learning, whenever you hear the term linear, like linear regression, and it means like it is linear in parameters, theta parameters, or like sometimes W is used. So it is linear in those parameters, not in phi. Like phi is used to represent features. Features can be non-linear. So is it possible to use the LSTDQ method in such scenarios also? Yes, you can use it because features can be nonlinear. You can have like suppose initially we were having this x coordinate. You could have used x cube also. So it doesn't matter. But the only condition in these linear methods is that these parameters should be linear. Like it could be like theta 1 x cube plus theta 2 y square. So still it remains linear because it is seen in terms of these parameters. As long as like these are not square or some other non-linear, then it remains linear because it is linear in parameters, not in features. So this you need to be aware of. Now, if there is no doubt, I'll move to the next question. So, which among the following statements about LSTD and LSTDQ methods are correct? So LSTD learns the state value function. Yeah, state value like default, like generally we say it as value function, but sometimes people call this V function as state value function also. So yeah, LSTD learns state value function and LSTDQ learns the action value function, which is Q. This is also true. Both LSTD and LSTDQ can reuse samples. Can they use reuse samples? No, because like they cannot use samples because it has to be on policy. If we like kind of reuse already seen samples, then we will no longer be on policy. We will be moving to an off policy kind of setup. So we cannot reuse samples like that. One sample suppose is like this SA S dash. So this you might have seen in past. Suppose at 10 step t minus 10. Then if you want to use it at current time, then essentially you will be moving off policy. Obviously, like if a policy dictates that you see this sample again, then you can do it. But you cannot, in general, you cannot reuse it. Like whatever is appearing on while moving on policy, you can use that, but you cannot simply store those transitions. And like this is talking about these two methods specifically because these two have to be on policy. So in on policy, we cannot reuse samples. So both LSTD and LSTDQ can be used along with tabular representation of value. Yeah, like we can use these two methods simply like we will use indicator function. Like remember, like there will be like a lot of indicator functions. Suppose if we are using value function and there will be indicator function corresponding to like how many states are there. So that many indicator functions will be there and only one of them will light up when we are considering that state. So essentially we can use this with tabular representation also. If there is no doubt, then I'll move to the next one. So again, like this is like kind of solving question. So consider the 5-state random walk task described in the book. So you might remember this task. I'll describe it again. There are 5 states: S1, S2 to S5. Suppose I'll construct the MDP. This is S1, S2, S3, S4, S5. Okay. There are two terminal states at each end. Suppose two terminal states are also there. Okay. With a reward of +1 for terminating on the right. Okay. So if we terminate here, like we get a reward of +1 on the right after S5 and a reward of 0 for all other transitions, including the one terminating on the left after S1. So this also has a reward of 0. and all other transitions also have a reward of 0. So let's make all other transitions also, and like the actions are basically you can move left or right only. So here like you have moved left. So terminal states are like we don't model transitions from terminal states because there are no outgoing transitions from terminal state. You can only come in terminal state. So this will be 0 also. This will be 0. This will be 0. And this will be 0 again. This will be 0. And this will be 0. This will be 0. And this will be 0. So the only reward which we are getting is if we are moving from S5 to this terminal state. This problem you can think of like suppose you want to, this is your destination. You want to reach some place. And for all other like points in space, you will give 0. When you reach the destination itself, you will give +1. So this is the setup of the problem. Now the question they are asking is in designing a linear function approximator. Suppose if we use a linear function approximator, what is the least number of state features required to represent the value of equiprobable random policy? So like you remember like we had this features phi I of state and where I is equals to 1 to k. So basically they are asking what is the least number of features which we can use to represent the value of the equiprobable random policy. So value, suppose if our feature is like um, we want basically a mapping from state to this value function, which will be in a real value. And we want to know like how many like this k are sufficient for that. Okay, so this is the like setup of the problem. Now one more thing, like you can assume like gamma 2v1 is common factor. And the like the policy is equiprobable. So equiprobable means like with 50% probable 50% chance you can go left, 50% chance you can go right. So and it's random policy. So since there are only two actions, we can kind of solve this problem. So you might remember the Bellman equations, right? So Bellman equations basically suppose we can express, suppose we write the Bellman equation for all the states. So like this used to be V of S1. So for simplicity, I'm referring it as V of 1. So this basically means value of state 1. So suppose value of state 1, what will it be? So it can go with half probability, it can go to S2, with half probability, it can like value of S1, right? We are talking about S1. So half probability it can go to terminal state, and with half probability it can go to S2 state. So let's write this. So half probability plus half. Now what will be the reward? In both the cases we are getting reward is 0. And gamma we have assumed to be 1, right? So gamma is 1. So terminal state value is always 0 because we don't have any outgoing transition from terminal state. But the value of this second state S2, like we denote the value by V2. So that will have some value. We don't know that. So this will make this an equation. So from here, like we can get, if we simplify it, what will we get? 2v1 is equals to v2. So this is our one equation. Now similarly, like in same way, we can write the equation for other states also. So for suppose for v2, but remember like here, like now we are not going in terminal state. So there will be a V1 and with half probability we can go to V3 also. So this will be another equation. So this will give 2V2 is equals to V1 plus V3. So this is another equation which we got. So in total, like we will get around 5 equations and there are 5 variables. So let's write for similar like V3 and these will be symmetric. So you can get the idea from there. So with half probability, you can go to V2. With half probability, you can go to. Remember, I'm not using gamma. Gamma is 1, and this is the reward. So in the initial phases, all the reward are 0. So I'm blindly writing it as 0, and you can go to V2 also. So 2V3 is equals to V2 plus, no, V2 plus, you can go to, this will go to 4, V2 plus V4. So if you go left, then you go to V2, right, then to V4 from V3. Similarly for V4, you can go half probability 0 plus 2 V3 and half probability 0 to V5. And similar manner, you can write 2V4 is equals to V3 plus V5. So this is all like fourth equations. Now we will write the value of state number 5. So half probability you can go left and collect a reward of 0 and you will go to V4. But with half probability, now you will collect a reward. Remember, like this is the reward. With half probability, you are going to this terminal state. You will collect a reward, but the value of the terminal state itself is 0. So now the equation will become 2V5 is equals to V4 plus 1. So you have like a set of 5 equations, linear equations, and 5 variables. So this is like usually solvable. So now like our goal is to like kind of solve these equations. So maybe if you guys want to solve it parallelly, you can also try to solve them. So these are the like 5 equations for us. So what I'll do first is I'll like kind of sum all 5 equations. Okay, let's do this. So when I sum it up, so it will be 2 times V1 plus V2 plus V3 plus V4 plus V5. So I'll write this 2 times V1 plus V2 plus V3 plus V4 plus V5. And on right hand side, we will have like this. V1 will appear once, right? V2 will appear twice, V3 will appear twice, V4 will appear twice, V5 will appear once, and 1 will appear once. So I will essentially have V1 plus 2V2 plus 2V3 plus 2V4 plus V5. This appear only once. And you can like simultaneously cut this V2, V3, V4, like because it has multiplied by 2. This also not. So it's essentially 2 times 2V1 plus 2V2 is equals to like 2V1 plus V5 equals to V1 plus V5 plus 1. So this basically means that V1 plus V5 equals to 1. Right, and two are here, like 1 is here, so I subtract it. So this we can label as equation number 1. So we have got an equation in V1 and V5 now. Now we want to get another equation in V1 and V5 so that we can solve it off. So how we can do that? Suppose we know from here, like V2 equals to 2V1. Now we push that here. So basically here, like we will put this value of V2. So it will become 4V1, right? It will become 4V1 and is equals to V1 plus V3. From here we get V3 equals to 3V1. So V2 already we know is equals to 2V1. V3 is equals to 3V1. Okay, so V3 is equals to 3V1. This we got from here and we put it here. So it will be 6V1 is equals to, and V2 we know is equals to 2V1 plus V4. So we get V4 equals to 4V1. Okay, and now we put V4 V4 is 4V1. So here, so it will be 8V1. V3 we know is like how much? 3V1. So is equals to 3V1 plus V5. From here we get V5 equals to 5V1. Now we have got like one more relation in V1 and V5. We can put simply this in here. So what we will get? V1 plus 5V1 is 6V1 is equals to 1. So V1 is equals to 1 by 6. So the value of V1 is 1 by 6. This is simply solving of Bellman equation. And similarly, you can get V2 is equals to 2 by 6, V3 is equals to 3 by 6, V4 is equals to 4 by 6, and V5 is equals to 5 by 6. So this is basically the value of all 5 states. Now we have values of all 5 states. For S1, we have 1 by 6. For S2, we have 2 by 6. This we have 3 by 6, this we have 4 by 6, and this we have 5 by 6. What they are asking is what is the least number of state features required to represent the value of equiprobable random policy. So this like we have like used the Bellman equations in a equiprobable random policy fashion only, because remember we were distributing half of probability to both sides. Now they are asking what is the least number of state features to represent this value. So basically, like we are mapping this to this, right? S1 will be mapped to 1 by 6, S2 to 2 by 6, S3 to 3 by 6, S4 to 4 by 6, S5 to S by 6, 5 by 6. So basically, like all we need is just the index of the state, right? If we know that the index of the state is 1, so we can write the suppose value of suppose state R is equals to R upon 6. So only one feature, just the index of the state is sufficient. So this is the one feature. So how many features are sufficient? One, just one feature. If you have just one feature, then you can do this approximation. I hope like you got this, but this also tries to explain that you need to like remember these equations, like these Bellman equations can pop up anytime. So you need to remember them, and they will be used for solving questions, even like in upcoming topics also. So if there is no more doubt, I'll move to the next question. Again, like this is also something related to solving. So, okay. So this is in an MDP with three states. So we are having an MDP with three states, S1, S2, S3, and a policy pi. So that V pi of S1. So this is the like truth. Two value function is given to us. Like V pi of S1 is 4, V pi of S2 is 6, and V pi of S3 is minus 1. And they have also given under pi, under this policy pi, the steady state this probability of being in S1 is half, and in S2 and S3 is 1 by 4 each. So this sum to 1, right? So suppose there are three states. So if you like keep on roaming around in these states a large number of times, then essentially the probability that at some point of time you are in S1 is half, and you are in, suppose this is S1, S2, S3. Suppose you are in S2 or S3, this will be 1 by 4 and 1 by 4. So this is the steady state distribution of probability. And a learning agent seeks to approximate B pi S. So this is the like it is using a linear parameterization. So this is like F is some feature of state. So dot means like could have used S also. So this corresponds to any state. So there are like two parameters W1 and W2, and this is one feature F. So this is a state feature, and W1, W2 are weights to learn. So features for the three state are as follows. So they have given us value of features also. So for the state one, it's 2, for the state 2, it's 1, and for the state 3, it's minus 1. So we have the value of states. I think there is something to check. Maybe I'll see. Okay, nothing. So they have given us value of features also. So if now the question is if the agent performs TD1 updates. So you remember TD1 states updates are essentially equivalent to Monte Carlo updates. So if we use this linear generalization scheme, what values will W1 and W2 converge to? So if you remember correctly, like in Monte Carlo estimate, like if we use like these TD1 updates, which is essentially Monte Carlo updates, like we converge to least square estimate, right? So what we have to do in this problem, we have our estimated this v function. We are given the true function. We will solve the least square error and minimize it. And whatever like W1 and W2 we get from here, those will be the values. So this is all you have to do. But one thing to take care is that like here, all the states won't get the same probability because like the steady state probability of being in all three states is different. So for, it's 1 by 2 for S1 and 1 by 4 and 1 by 4 for S2 and S3. So you will essentially weight the error terms of those values by these probabilities also. So our objective function basically becomes so half, like I'll write it this way, plus 1 by 4 plus 1 by 4. So this will be error term of first. So first state, like what is our estimate? So feature value is given as 2 and 2 W1 plus W2. This is our estimate. And what is the ground truth? Ground truth is 4. So this is the actual value of this state. So we are like basically using least square error. So it will be a square. And this is our estimate and this is the actual truth. So the difference is the error. Now second state. For second state we have feature value as 1. So it essentially becomes W1 plus W2, and the ground truth is 6. So minus 6. And again, a square, since we are using squared error. We are using squared error because this Monte Carlo converges to that least square estimate. Now what we want to do is for the third one. For third one, the feature value is -1, so it becomes minus W1 plus W2 minus W1 plus W2, and the ground truth is how much? -5. So minus minus 5 becomes plus 5, right? So square. So this is like our combined objective function. So this, suppose if I call this entire thing as O. So this is our objective function. And now what we have to do is we have to minimize this objective. Our domain, we need to basically find out the values of W1 and W2, which minimize this objective. And how we can do that simply is by taking the gradient, like here you can take the partial derivatives since there are only two variables, so you can like basically do du by dw1 like this equals to 0, and with respect to w2 also equate it to 0. You will get some equations and you will need to solve them and get the values of w1 and w2. So this is essentially like the essence of the problem. Now like I'll describe, like I'll actually do this calculation, so you are also like you can do this simultaneously also. Maybe I'll see like how many people are there. Okay, so there is only one, so maybe I'll do it. Others will be watching the recording. So this is our objective function, right? So first, like we need to take the derivative with respect to W1. So again, like you know this derivative, so this 2 will come here, so it will essentially become 2 upon 2. Then we have this term, this will remain one time, and then we take again like chain, apply the chain rule, then one more 2 will come. So essentially it becomes 2W1 plus W2 minus 4 and into 2. So this is for like first state. Now for second state, again, like we will have this 2 will come here after derivating with respect to, and with chain rule, like there will be no impact because the coefficient is not there. The coefficient is basically 1. So it will be 2 by 4 times this term. So plus 2 by 4 times W1 plus W2 minus 6. Okay, and similarly for this one, but here like coefficient is -1, so that will factor in, and it will become plus 2 by 4 minus W1. So we can like get this minus inside because there will be only one term. So W1 minus W2 minus W5. W1 minus W2 minus W5. Okay, so this is our that thing. So this becomes basically half. You can write like half, and this either way like we have to equate it to 0, right? So we can take these denominators and move them, like multiply them and this 0. So essentially our like remaining equation becomes like this 2 will remain, this denominator is gone now. So once this is gone, so it becomes 4W1 plus 2W2. No, there is one more 2 right here. So there is one more 2, so that makes it 8. This will be 4, 16, right? It will be 16. So this term is 8W1 plus 4W2 minus 16. This will be simply W1 plus W2 minus 6. And this will be W1 minus W2. What was this? This was 5, not W5. Minus 5. So essentially W2, this goes from here and it becomes how much? 8, 9, 10. 10 W1. W2 remaining are ones plus 4 W2 minus 16 minus 6 22 and 5 27. So essentially you get this that side. So this is our like first equation between W1 and W2. So this is the one equation which we got. Now like for second equation we need to do this derivative of O with respect to W2. This is like with respect to W1. So let's do that also. So here again, like with respect to W2, like like with chain rule, like the coefficient is always one. So that will never come in chain rule. So essentially we take like two here and just keep the remaining terms. So it will be 2 upon 2 uh 2 W1 plus W2 minus 4. It was this only 2W1 plus W2 minus 4. 2 came here, 2 upon 2. Then 2 by 4 W1 plus W2 minus 6. Again like 2 by 4, but this time it will be minus W1 plus W2 plus 5. Okay, minus 1 won't come because we are taking derivative with respect to W2. Essentially, this is 1 by 2 again. This is also 1 by 2. So again, like we have to equate it to 0. We can either assign this to denominator to this multiply it by 0. So this is also 1. This is also 1. So what we have left is 4 W1 plus 2 W2 minus 8. And here we have W1 plus W2 minus 6. And here again minus W1 plus W2 plus 5. Here W1 will get cancelled. So essentially we have 4 W1 and I mean W2 2 plus 3 plus 4, 4 W2, and this is 8 and 6, 14, and that's 9. So minus 9, we send it that side. So it will be, this is our like second equation. So we have two equations in W1 and W2 and two linear equations. So we can solve them easily. So let me write it on this slide. 10 W1 plus 4 W2 is equals to 27. It was this only 10 W1 plus 4 W2 is equals to 27. And the second equation is 4 W1 plus 4 W2 equals to 9. 4 W1 plus 4 W2 is equals to 9. So you solve them. Simply subtract, this will get cancelled. 6 W1 is equals to 18 implies W1 and is equals to 18 by 6. Okay. Now we have 3. You can put this value here and it's essentially 12 plus 4 W2 is equals to 9. So 4 W2 is equals to minus 3. W2 is equals to minus 3 by 4. So W1 we have got 3. W2 we have got minus 3 by 4. So what is the option? 3 and minus 3 by 4. Okay. So this is the correct option here. 3 and minus 3 by 4. Okay, so I hope like you got this question. If there is no doubt, like I'll move to the next section, which is demo. So in demo today, we have fitted Q equations. So till now, like the thing was like most of the codes were like which we could were able to execute in like real time, kind of like they didn't take much to finish running. So but from now on, like since we are moving to a regime where like we need to have those classifiers, regressors, train them, update them, or like later we will have deep neural networks also come in. So now from now onwards, like training them like during the session and getting the values like will be difficult. So what I'll do is I have already like run the file. So I'll be simply showing the outputs, what the output it gave. And for this week, I have fitted Q equation, and this is like I have taken from a reputed researcher in the field of RL. So maybe now I'll share this. So are you able to see this screen now? Like the browser?
Yes, sir. Yes, sir.
Okay, okay. Thanks. So now like this is like fitted Q equation, and this basically I have taken from this RL summer school. So this is actually a like 10-day program. It happens every year. I'm not sure like whether it will happen this year, but here like generally like the people who have some knowledge of RL can like go there and have some more sessions on each of the topics. Basically, like some new topics also. So good thing is like they have this videos of the lectures also available. So if you are interested, you can like see them, like the topics which like you have already now you are familiar with these topics. So you should be able to like watch these talks and learn more from them. So again, like this notebook, like this is not by me, like this I have borrowed from this RL summer school, and it's from this GitHub repository. And this person, like A. Refn, like he is actually one of the creator of stable baselines tree, which is a very popular RL implementations for various algorithm. So generally in machine learning, we have scikit-learn, and in RL, we have stable baselines third version. So in this notebook, like we will be using fitted Q equation to solve the card pole problem. So what is this card pole problem? Yeah, explain. So this is card pole. So basically like there is a cart and on that like there is a pole. So but this pole might fall down. So you need to like either move left or right in order to balance this pole so that this pole doesn't fall off. And based on that, if this pole never falls, like you get a reward of +1. So this is the problem. And action space are like you can push the card to left or push the card to right. Observation space, you can observe like these four. There are four observations. What is the card position, velocity, angle of the pole, and pole angular velocity. So these are the like range also like they can take values. So some of them, like most of the, all of them in fact are continuous. So this goes from -4.8 to 4.8 position and velocity -infinity to infinity. Obviously like it won't go to infinity, but like this basically means it can take any real value. And pole angle is like it's in variance. So you can have from -0.418 radian. It basically -24 degree to 24 degree, and also the pole angular velocity. So these are the like four state features for you. And on based on that, these state features, you need to come up with some action, like whether you can go left or right. And the goal is like you don't uh, let this pole fall off from the car. And reward, since the goal is to keep the pole upright for as long as possible, a reward +1. Okay, so there is like reward for every time step, +1 reward for every time step. So suppose if there are 100 time steps and you manage to keep the pole straight, like the pole doesn't fall for all the 100 steps, so essentially you'll get +100. For every step, like you'll get a +1 if the pole doesn't fall. Otherwise, like it will terminate. Also I think like there will be a truncation also, like because like eventually you need to terminate, like if you like are able to keep the pole on like without falling for 500 steps, then the episode will terminate. If the pole falls, then definitely episode can terminate at that point itself. But also like there are some other conditions also. If pole angle is greater than ±12 degree, then episode will terminate, because this will essentially mean that no matter how like how much action you take, like no matter you go left or no matter you go right, this pole will fall. So it has reached certain threshold according to the dynamics of the system. And maybe if the card position is greater than ±2.4, then also. So basically, like this means that this card basically reaches this point or this point. So then also episode terminates. So this is the like basic description of the problem. And also one more thing to notice, like you might think that start state will be something always, start state can be random. So you can start in any state. The pole might be tilted already, the cart might be here. So any start state is possible and you need to learn like how to like keep the pole from falling. So this is the basic task which is going to be covered in this notebook. So again, like I'll mention, like I have taken this from this Arvel Summer School. And so this is simply installation of Jupyter Direct for auto formatting and some installing of dependencies. So again, like this I have already run like in morning only, so it runs fine. So I'll be sharing this with you also. So the thing is like they have a lot of comments also, like which you can read to learn better. So generally, like in this gym interface, like there are three functions. Reset basically means suppose an episode has terminated, then we call this reset function. and it will like kind of reset to the beginning of the episode. It basically like this returns a start state for us. Observation basically means a state here. So it returns a start state and some dictionary with additional info. Generally, like we won't be using this dictionary. And step means like step, when we take this step, we give an action to the this step function, and it will basically take that action in the environment and come up with what is the reward and what is the like next state also. And also it will mention whether like we have terminated or truncated. Truncated means that the maximum number of times test, which was 500, is reached, and the episode is finished. Like this is denoted by this terminal state. So all these like what is written by this step function, we will be seeing in detail later. So, but this is just to give a brief overview. And there is render, but like this generally doesn't work on Go Collapse, so leave it. So again, like there are some features like you can have this observation space and action space, and it basically mentioned like what is the dimensionality and whether it's discrete or continuous, all those details. So we will see this. So this is the environment. This you can see here. Like the goal is to balance this pole. So again, like if it goes there, episode terminates. So this is the library which we will be using to import this environment. So this is the card pole version one. So this is the environment which has been made, and as you can see, like this is the shape of the. So we have already seen in the description of the environment that there are four state features. So this is the state features. Like observation space basically means the state space. So state space shape of it is four, and these are the, you remember those values. So these are the values. So this basically, you remember like we saw minus infinity. So this is the like the maximum value which Python variable can store. So in that sense, it's indicative of minus infinity to basically plus infinity here. So this is like the first one is the minimum range of all four, and this is the maximum like value of all four features. So those velocity and position features. And action space is discrete with two actions. Either you go left or you go right. So this method you can call reset at the beginning of the episode. And what it does is it will return an observation. Observation basically means state. It will basically return a start state for you to begin with, because you need to take an action. And for taking an action, you need to be in some state. So that start state is returned by this reset. And if you want to sample a random action, which we will be using in this fitted queue equation, because fitted queue equation basically like you have to sample randomly enough so that like you have a fair amount of idea about all the samples. So when you want to sample a random action, you simply call this environment.action space.sample, and it will return. Since we are having only two actions, so it will return either left or right. So like one of them is mapped to 0 and other one is mapped to 1. I think left is mapped to 0 and right is mapped to 1. So now this is the step function which I was talking about. When you call this step function and pass the action, it will return you next state. Observation is the next state. Reward, whatever you got. Whether episode got terminated. So episode could get terminated due to like either like the pole falls or like pole is at certain maybe beyond 12 degrees. So all those conditions were there. So then the episode will terminate. It will return whether the episode has actually terminated or it is still going on. And truncated means like you have passed those 510 steps. So someone is asking how much time it takes to compile and execute. I don't exactly remember. I ran it. I think that detail is known, but I think like around 10 minutes you can see. So like you can run. So I like ran it like uh, I didn't run it completely. I ran it like step by step, like each cell at one time. So I didn't don't know how much time it took in aggregate, but if you do runtime and run all, then it might take around more than 10 minutes, because like there are some functions which will require training and all those things. So this is the step function, and like basically they are printing. So initially like this is the like shape of our observable state space. Four state features are there, then the reward like this like they took some random action and it got give a reward of 1, and terminated truncated are like boolean variables, like it hasn't terminated, not truncated, and info is a dictionary, which either way we want to be using. So the you remember fitted queue iteration algorithm. So in fitted queue iteration, maybe I'll use Jamboard. So first, like we were collecting some sample. Suppose you have initialized this Q0, maybe like as 0, all the like state action pair, the action values are 0. Then like you'll like kind of collect some data from it, and then like you'll data, and then once you collect that data, so then you'll like kind of train some regressor, right? And this regressor will be your Q1 now. Now again, using this, you will collect some more data and you will use that data to train another regressor. This will be Q2. And this will keep on happening again and again. You will use this. So this is like one iteration, second iteration. And in this way, like these iterations will go on. So that is why it's called fitted queue iteration, because you are like fitting a regressor also. Can be a classifier also, but we are using regressor. We are actually using regressor, yeah. So KNN regressor is used in this task because like essentially like we need to estimate the Q value. So suppose we are in state S, then we need to have the Q value of left and then Q value of state and right. So these are the two like actions for us, and for every state we need to estimate this Q value. So like till now, like we have seen value function based approaches. So in value function based approaches, what happens is we value function approaches, like generally if we want to do control, what we will do is we will suppose I'll give you just an example. Suppose we have four features. These are our like whatever position was there and velocity was there and there was angle and there was angular velocity. These four are our features. And in between, like there are some hidden layers. I want to all the connections. So there are some hidden layers. You can think like this is our neural network. So this is just for example. So suppose if our output layer like need to have we have two actions, like one corresponding to left and one corresponding to right. So these are our two actions. So basically what this value function approach does is it will like learn a queue function. So this network is, you can call it DQN, because like this will come up in next lecture also, deep queue network. So you are passing the state features and the goal is to learn the queue values of corresponding to each action. So suppose this is for left, so there will be a real value here, there will be a real value here. Like neural networks, like they can input in maybe some range, then you can map them to the real space also. That is also possible. But the point I'm trying to make is like these value function based approaches are two-step. First, you learn the Q value function, and then essentially because you will need the policy to act in the environment, because policy is the mapping from state to action. So you will either way need this policy. So for each state, what you do this argmax over all actions and a queue of SA. And this will basically return you the best action. There will be a set of best action. So this essentially is a two-step process. First, you learn the Q value function, then you take the argmax to get the best action. And this will essentially mean your policy. So this is the like kind of approach in value function based approaches. So I'll see chat once. So the point I'm trying to make is that value function based approaches are two-step approaches. And then in next week, you will learn something about policy based approach. So in policy-based approaches, what will happen? You will pass these features. You will have like all those hidden layers and all. In the end, suppose we have two actions. What it will return? It won't return a Q value. It will return maybe a sigmoid. You can take a sigmoid between 0 and 1, and whichever like action, like you can simply like directly learn which action to take. So this is one step process. So you are simply mapping state to action here, but there first you were learning Q values, and then from Q values you are going to policy pi. Here like this is simple mapping of state to action directly. So this is known as policy network. So this is like kind of advantageous for us policy network, because like sometimes we don't want to do this two-step approach, and there are some downsides of this two-step approaches also. One biggest downside is like it cannot work in continuous action spaces. So value based methods, like limitations, continuous action spaces. Although like continuous state spaces we can model by like having these, you can pass like continuous values for each the features in the neural network. But what happens in value function, suppose if you have like infinite number of actions, and you cannot have infinite nodes here for each action. But if suppose our action is continuous, suppose in policy network, if the action is, suppose you want to last one like carpool example was discrete one, so I'll give more example policy. Suppose you have those X, Y, Z coordinate as your features to the network, and the goal is to action is like kind of velocity. So you have this network like in between, like there will be hidden layers and all. Like you can draw this, but the this neural network can simply predict a continuous action. So policy network like these are this is the advantage of policy approaches. Like they can work very well in like continuous action spaces, whereas value function based approaches generally don't work well. So there is one more concept which you remember this one. To mention this, you can have either like this kind of S comma A. You can pass both of these in the network. So what we were doing is before it was like action was in the like one node for each action. Here you can have like you can pass the action also in the, suppose these are states. Till here like state features are there, and you can pass the action in here. But the issue now will arise. Suppose now you will have suppose one Q value. You are passing state also, action also here. But the issue now arises in this. Suppose you have this second step in policy. When you want to take argmax over all the possible actions, and you will have to like call this again and again for each action. Then essentially, if the action space is infinite, then you will have to call it infinitely and then take the argmax. So this is the like disadvantages of value function based approaches. So if you use like um, one node for each action in the last layer, then the issue arises at the first step itself. Like that when you are getting the value Q values of each action. There like the issue is like you cannot have infinite nodes for infinite actions. And if you like pass the action as one of the input and get a continuous value as the output, then the issue will arise in the second step. That when you want to take argmax, you'll have to take argmax over all the actions. Then if you have to do this for all the actions, then what will happen is like you need to call this for each action, each possible action, and then only you can have that argmax, right? Overall actions. So essentially, these are the like downfalls of value function based approaches, but policy based approaches you can simply map to the action directly. There is no like two-step thing. You can simply get the answer. Suppose if your code XYZ is 1, 2, 3, and you it can give a velocity of maybe 5 meter per second. So this can be continuously. So I hope like you got this idea. Now I'll go back to the demo. So this is the like function which is basically collecting data. So and this we are at this step, right? So you remember initially we have initialized it to be 0. I'll show it later where like the action value function has been initialized to 0 for all state action pairs. But initially like we need some initial data. and this is the that process. So we are collecting some initial data. So they have defined one class like of offline data, and it contains some arrays, observations, basically state. These are the states, these are the next set of states, these are the action, and these are the rewards. And also like there is one more array which contains information of whether the episode has terminated or not. So essentially it's SAR dash, and also one more additional array which mentioned whether the episode terminated or not. So this is the function for collecting data. And what it takes as input is environment ID. So this will be like cardpool version one that string we saw, and number of steps, like how many like data points you need. So 50,000 steps means that you will have like 50,000 length arrays here. So this is the environment. You have created this environment. Now this is what I was talking about, that initially like you have this observations. So these are like arrays which will store these values. So initially they have initialize everything to zero, states zero, actions zero. So essentially we will be taking around 50,000 steps. So for 50,000, like this will be first dimension of this array. And secondly, like for each step, like we will have like four values. Like remember those position, velocity, angular velocity, and angle. So all four we will need. So this will be like essentially four here. So it will be 50,000 into four. This will also be 50,000 into four array. And actions will be like simply like we can take either left or right. So simply 50,000. Similarly, reward we can get plus one or no reward. So it will be just 50,000. Terminated, you can either terminate for each like transition or not. So similarly, and done is initially false. So done basically means whether the episode has terminated. You can terminate either like if the episode has actually terminated, or you can terminate by like that limit of 500 time steps has passed. So terminated means like your pole has fallen off. Truncated means like you have reached the maximum time limit. So this done variable basically means that it denotes whether the episode is done or not. So now we are doing the first episode here. So first episode basically initially we will need this start state. So this start state is coming from this reset here. Now what you are doing is for each, like this is the iterator variable IDX in n steps. For each of the step, what you are doing is you are collecting the data, and you are sampling a random action, because like you remember in fitted queue iteration you need to have randomly generated data so that you can like have a good approximation of everything. So action, you have sampled it in a random manner from the environment, and then you'll like take this action and get the next state reward, whether it's terminated, truncated. Info like basically is a dictionary which we won't be needing either way. Then you are like storing this transition. So you remember this, these arrays are there. So we are storing this. So in observations array, we put this at this index, and then we put next observation, actions, rewards, terminated also. And now we will move to the next state. So here like our current state, so observation denotes state. So like people use these terms exchangeably. Sometimes like it makes sense to call it observation in robot domain and all, like, but in literature it's a state. So we are basically moving to the next state now. So we have like collected this transition. Now we are moving to the next state. So this basically means like we will move to next step. So essentially like this is the end of our loop. And we also check one more condition. If like episode is done, like at any point of time, like if episode is terminated, like done is basically either terminated or truncated. If it's done, then we will reset the environment so that we get a new state as the initial start state. So this is the basic function here. And what it returns is offline data. So remember we made this class offline data. It contains these five arrays. So here like they have like returned this instance of the class and with like all these five arrays. So this will be returned. So this is simply the definition of the function. We will be calling it in the next one. So this is the like, remember like this function takes two inputs, environment ID and the number of steps. So here like 50,000 was the default number of steps. If like you don't pass anything, then it will take 50,000. So here, like number of steps is 50,000, environment ID is blackboard version 1, and now we are actually calling the collect data function. And this will like return us the offline data. So this we are storing in this variable data. So this we have collected the data. Now these are simple checks just to see whether like the data generated is actually correct or not. So we know like the number of states should be equal to this one. Number of states should be equal to number of steps, basically 50,000 because we know 50,000 transitions are needed. Number of actions will also be same as. So since like this one is printing nothing, basically means nothing, no error is there. If there was some mismatch, then it would have like thrown out any error. So since there is no error, this means that all these checks are passed. Also, they are checking whether like there are multiple episodes. So they are basically checking that whether like there is some terminated or not. Any of the episode has terminated. So all those checks are there and environment ID, like they are checking. Now they are checking at a more granular level where like they are seeing whether the each of the state has like four features. And this is for state and this is for next state. And also they are checking that the shapes of the arrays are perfectly fine as we have defined. So all that thing is done. Now also like they are storing this data as some output file. So remember this output file name. So this variable we will be using again later. So this data like they have like collected and stored it. So eventually like since I'm not connected to runtime, but like once it is collected data, it will show up here somewhere here. Now this they have stored. Now we move to the actual predictive equation algorithm. This is like the you remember this is the first data set which we have collected till now. Now we actually need to train a regressor for this Q values. So let's go there. So these are like simple libraries. So as I mentioned before also that for traditional machine learning like this sklearn library is there, like a lot of people use it for reinforcement learning. The analogous thing is table baselines. So we use that. So now the thing is you have to choose a model. Like you remember, like you need to have this Q, like this approximator, function approximator. You will give state as the input, and basically you need Q values for each of the state. So here, like you could have used a neural network or some other model, but here in this notebook they have used K nearest neighbor regression. So you might have heard of K nearest neighbor. So what happens in K nearest neighbor is this. So suppose like there are a lot of data points. So in discrete case, suppose these are minus, minus, suppose some, there are, suppose we are considering two classes. Some of them are minus, some of them are plus. And now we want to find the level of this data point. So we will like draw some predictive, suppose we will collect the nearest two neighbors of it. Suppose if k nearest neighbor k equals to 2, and we will collect two nearest neighbors of it and see like what are their labels. And on the basis since it was minus for this, so we will put minus for this also. So this is in classification setting where like we have two classes, but in regression setting we will be taking average of it. Average of these will be real, having real values as labels. So we will simply take average of that and assign that level to this one. So this is the basic concept of k nearest regressor. So here like they have simply used number of neighbors to 30, and this is the regressor. Now like these are some files imports happening, like these are the environment ID. Now remember this output file name. So we are having that vendor mode and creating the environment basically and loading the save transitions. So we saved it at this location and we are loading the data now. So now begins the first iteration of the this one. So you remember like we need to train a regressor which will essentially some kind of model which will take as input our state. Maybe four features were there, and for both these state it will return some q value. So this is our kind of here state action. So this is for left, this is for right. So it will return some value for both of this, and this will be q value. So either way state is coming from here, and for each action we will have some value. Now So at initial step, like you remember, like in fitted Q equation, our targets used to be R plus gamma times Q. Now the issue is like initially we have initialized our Q to be all zeros, right? So this term won't appear in first situation because like all our Q values are zero. You can take whatever, like it will be zero. So our target will be in this case, first case will be only reward. But from the next situation, we will start considering this Q also. So that's why like they have used just this is our like input. Okay, so they are giving, they have used slightly different setup. So instead of having like, they are also passing the action also here and getting one value, Q value here. So what will happen, like they will call this twice, once with left and once will right. So these are the two approaches which are generally popular. So this is our like kind of training data, state and action at each, like we collected around 50,000 transitions. So for those 50,000 transition, what was the state, what was the action, and what was the reward? So this is the mapping which is being learned by this regression model. So we have this targets, simply copy of rewards initially, because you remember like this term is initial Q SARS, for us. And we are having this, we are like basically fitting this data. So this model fitting function is there, and you are passing this current observation input, basically like observations and actions, you have concatenated them. This is the input and this is the output targets. So this is our X and this is our Y. So they are fitting this. Now after fitting, like you need to write the function to predict the Q values. So this will be like for predicting the Q value. So this function basically takes this model as the input. So this is simply a utility function and an observation. So this is basic model, trained model. Now you, what you want to do is use this trained model to generate, remember this fitted Q equation. So you have like fitted this model, you have reached this Q1 stage. Now this Q1 stage, now you need to collect this data through this Q1. So now for in order to do that, we are writing this function Q value. So this model will be passed here, observations will be passed, actions will be, number of actions will be passed, and it will return these Q values. So here, like they are using some batch concept. So basically, like this notebook has been written with the perspective that you can change the environment and everything. Here, like they are using batch size as the length of observation space, which is 50,000. So that shouldn't matter, but you can use a smaller batch size. Either way, it will be looping over batch sizes also. And this is the Q value. So initially, we have assigned it to be all zeros and batch size and number of actions. Now for each action, like basically we are having, so this is just for processing purpose only. We are like using this model to predict the Q values. So we will get some predicted Q values and it will like basically store at the action index and like return those Q values. So basically like now we have reached this stage. We have like kind of collected this data. Not yet, but like this is the function which will be used to collect the data. Now like they are like kind of testing it also. Now they are defining, this is simply to evaluate this, and for evaluating you can have these some episodes. So they are writing the function to evaluate a model, so you can evaluate it, and simultaneously like in this cell they are doing some, they are generating some videos, but you can ignore them. So this is like they have kind of written this evaluation function, and they are calculating what is the like episode reward and total reward and all those things. So this is like the result which we got. This is just for testing purpose. So they are basically testing how good their approximator is. Now like this we have done for initial this one. Now if you want to do this, like it's called fitted Q iteration because you need to do this again and again. So once you need to do this again and again, so you will be running it over n iterations. So it will be like you'll have this Q approximator and you will collect this data from it. And again, like from now onwards, our targets will be this gamma times this max. Because like since we are using Q learning setup, so we'll be using max over these actions, but they're like we use only reward because either way all the values are zero. So max will always be 0. So it's essentially random. So this will become our target now. And essentially we will learn the next function approximator. And again, like collect data from it, learn new approximator, collect data, and this will keep on going until you are like you are satisfied with the q value function. So now like they are actually doing it here for like they are doing for 20 iterations and they are also evaluating it. So gamma like discount factor they have taken 0.99 and then they do several iterations of FQA and it's essentially 20 here. So this is the maximum number of iterations and as you can see like with time the score is also improving. Initially it was 0.72 then became 0.86. So with iteration like we are learning better. So 0.9 0.92 again like at iteration 12 it became 93 94. So the maximum you can achieve is 1 year. So it got close to 0.94. That's essentially very good. So and that too in 20 iterations. So someone was asking like how much time it would take. So it essentially depends on this. This is the bottleneck. So if you increase this number of iterations to maybe 100, then it will take proportional time according to that. If 20 was taking some time, then it will take 5 times of that. So this you need to take care of. Like remaining cells are simply not that they don't take that much time, but this cell, like because you will be running this entire procedure again and again over iterations, so this will take some time. So this is simply for recording the video and showing the video. So this is like their video. So here we can see what this is the learned agent after 20 iteration. We can see like the hole doesn't fall, right? You can see this. So episode ended, now new state like see, this is like very good performance. Like it is basically balancing it. And now when time step ends, then it will terminate due to this truncation. So this is like the basic fitted queue iteration, which I have taken from GitHub of that person. And this is from other summer school. And so basically like this is like I have explained the fitted queue iteration, but like there are like a lot of comments and everything. So you can read through them also and just gain more insights. And beyond this, you can do something more. You can play with different models. So these guys like they use k-nearest regressor. You can use a neural network and play with their hyperparameters also. Remember, like k-nearest regressor has a hyperparameter of how many neighbors. So they took 30. So you can take different number of neighbors, or you can simply change the model itself. So play with the discount factor, they use 0.99. You can play with discount factor also and play with the number of data collected. So we collected 50,000. If you want to collect more, you can do that and see like basically more data means uh, we are basically near good performance. So as much data as possible which you can afford, you can collect that much and you can collect the combine data from random policy with data from trained model. So remember, like we were using random sampling to generate actions, like actions were sampled in a random manner. So you can combine that random policy with data from the trained model. So this will like eventually help in converging faster. So essentially in this notebook, like you have learned to collect data, how to collect data using a random agent in gym environment and predicting Q values using a regression model, which was k-nearest regression and the fitted queue iteration algorithm to learn from an offline data set. So this basically fitted queue iteration eventually moves into deep queue network, which will be covered in week 8. So I hope like you got this understanding of this algorithm, fitted queue iteration. So either way, like I'll be sharing this notebook with you. So remember like this is from this Swapo. So there must be some other tutorials also. You can see them deep queue network and there are other tutorials also. And suppose this is the whole environment. Okay. Yeah, so I think that's it on demo side. So now I'll like move back to the slides. So I hope like you are able to see the slides again.
Yes, sir. Yes, sir.
Okay, okay. So now, like, since the demo is covered, also like, I covered FQI. Like from now on, like these algorithms are rigorous, so you cannot cover all of them in like one session. So you can try out like those LSTD, LSTDQ, and least square policy equation. But the thing is like these are like slightly old. So nowadays, like most of the people go for deep RL. So like this is the like trend nowadays. So if you want, you can see them. If you don't want, you can try DeepRL. Either way, like I'll introduce you to DeepRL. Probably this course is slightly old. It was recorded in 2016. So a lot of developments have happened from 2016 to 2024. That portion is missing. So either way, like, but there are good blogs and everything. You can learn about DeepRL also.
Sir, if possible, kindly share some of the links for deep RL also in future, if possible.
Yeah, yeah. Basically, like I will be sharing in this slide only. So in the reading material section, I have a link and I'll basically introduce also.
So thank you very much, sir. Thank you.
Okay. So now we move to assignment 8. So assignment 8 basically means first question. This is the first question. So you are given a training set of vectors phi. Okay. So that each row of matrix phi corresponds to k attributes of a single training sample. Suppose that you are asked to find a linear function that minimizes the mean squared error for a given set of stationary targets by using linear regression. State true or false for the following statement. So the key term is here linear regression. If the column vectors of phi are linearly independent, phi is basically our feature matrix, or some people call it design matrix also. It's whatever, like one component. So if you can append this labels also to this design matrix. So state true or false. If the column vectors of phi are linearly independent, then there exists a unique linear function that minimizes the mean squared error. So you remember like the solution of linear regression is something like this. This is from traditional like basically machine learning course. This is not part of RL. So the linear regression solution is something like this. So this is the like optimal set of parameters. And basically like if these column vectors are independent. So essentially like this equation is something like this. Phi t phi theta is equals to phi t y. So this basically you get like when you formulate this linear regression problem and you formulate this objective mean squared error where mean squared error, then you take the gradient and equate it to zero and all this is happening in vector notation. So this is the basic thing which you'll end up in after derivating it and equating it to zero. But here like the while you need to obtain this theta. So you need to ensure that this is invertible. And this can be invertible if the column vectors of phi are linearly independent. So then this term becomes invertible and it goes on the right hand side and inverse. So if the column vectors are linearly independent, and this basically means that if it's invertible, then there will be a unique solution, and that unique solution will be this one. So this is true. So basically, like this is more like from a machine learning point of view, not really that much into RL. But either way, like you need to be aware of this also. So I gave the answer because like this was more from machine learning, but for other questions, I'll simply guide you through to the answers. So which of the following statements are true? So it's a multiple option correct. Function approximation allows us to deal with continuous action spaces. Like, yeah. So basically, like the major issue with tabular approach was this only. Like, you cannot have, suppose if you are storing value function, you cannot have like a long table which will store for each possible state. And this state can be like continuous and infinite. Infinite state, you cannot have infinite memory. So that was the limitation of the tabular approaches. Then we like move to these function approximation approaches. So basically, like they allow us to deal with continuous action spaces. Yes, that is true. So a lookup table is also a linear function approximator. This is also like kind of discussed in class. It is a linear function approximator. You will simply use indicator function. So for every state, you will have an indicator function, which will light up only when like we are considering that state. So now the question is like state aggregates do not overlap in coarse coding. So you need to so basically, this will be the deciding factor. So these two are either correct, first and second. So you need to see this whether state aggregates whether they overlap or do not overlap in coarse coding. You might remember this example, right? Was there any overlap or not? So based on that, you can get the answer. Either way, like none of the above want to get an answer. So if there is any doubt, you can ask me. Otherwise, I'll move to the next one. So next question says this: in which of the following cases the loss function, the loss of a function approximated as this. So this is basically our approx or whatever like estimated, and this is the truth. So in which of the following cases the loss of a function approximator, so this loss will lead to poor performance. And consider relevant states to be those which are visited frequently when visiting when executing near optimal policies. Okay, so we are executing near optimal policies, almost optimal, and relevant states are those states which are visited very frequently in these near optimal policies. So, in which of the case like this loss will lead to poor performance? Large state spaces with a small percentage of relevant states. So, state space is very large. So, there are maybe suppose consider 10 raised to power 8 states, out of which maybe just 10 is to power 1 states are relevant, just 10 states, not 10, like this will be too late. Maybe 1,000 states are relevant. Okay, so what will happen? Like this loss will basically like be giving priority of like these, like these will have much larger weight and contribution to this loss function because it's simply sigma over all the states. It's not considering any weight factor, right? Remember, like we saw one example in which we had those steady state distributions as the weights, but here it's not considering that. So this loss function is essentially giving uniform weightage to all the states. So in this case, you can clearly see that if like you are giving equal importance to states which are not very relevant, and these actual relevant states which are getting very frequently visited in near optimal policies, they are getting very like less contribution to this loss function. So much of the contribution is coming from this one. So in that case, like you can see, like it will result in poor performance. But if the small state space with large percentage of relevant states, then essentially if state space is like 1,000 and out of that maybe 8,000 are like relevant states, then it doesn't really matter because much of the contribution to this loss function will be coming from relevant states. So in that case, there won't be a poor performance. Obviously, there will be some degradation, but like not that much, like that you can label it as poor performance. Large state space with large percentage of relevant states. So if like we have like 10 raised to power 8 and then maybe 10 raised to power 7 into some maybe 8, these many relevant states, I mean like the contribution will be sufficient. So in this case also, we won't have issues. So basically the issue basically arises when like we have small percentage of relevant states. So obviously this cannot be the answer. So I hope like you get the answer from this. Now a Russian reason kind of question. So a Russian is it is not possible to use lookup tabular approaches these methods to solve continuous state or action problems. So remember I mentioned this vector, like if there are like suppose for value like you have these s1 s2 like till infinity, you cannot maintain this in memory. This is for value, but in case of continuous action spaces you will be maintaining a table. So it will be S1, S2 till infinity. And here like you will be having A1, A2 actions till infinity. And you will be having a cell. So this will be like using for Q function and this will be for value function. So you cannot use tabular approaches in those settings. So this is essentially true. It is not possible to use lookup table-based methods to solve continuous state or continuous action problems. And they have also mentioned that you assume that discretization of continuous space is not allowed. Sometimes what happens, like suppose the action is how much you should turn your steering wheel. Suppose this is the steering wheel of your car. So essentially you can turn between 0 to 360 degree. Uh, but the issue is here like you can discretize it. You can make like 360 continuous, like 360 discrete actions. Like you can 361 essentially. So you can discretize it. So some approaches do this, like, but here like we are losing some kind of information because we want to be having this 0.5 degrees. So that information is lost, but either way, like some people do it. In some problems, it's fine to do this discretization also. But here, like the assumption is that discretization is not allowed. Then obviously, lookup table-based methods cannot be used. It is not possible to use. So if it was discretized, then you could have maybe had like some 361 length, like 361 columns, and you could have discretized the state also in similar manner, some number. So that table would have been feasible, but continuous action without discretization, it is not possible to do in lookup table-based methods. So this is true. Now, the reason they have given is for continuous state or action space, there are infinite number of state actions. Yeah, like this is also true, right? Remember, even if your action is like in between 0 to 1, like there are infinite number of real numbers in 0 to 1 also. So for continuous state or action space, there are infinite number of states of action. This is also true. Now you need to see just that, whether this is the correct explanation or not. So either way, like these two are ruled out, but you need to see whether like the explanation is correct for the other issue. So now we move to again another assertion reason kind of question. So if there is any doubt, you can ask me. Otherwise, I'll move to this question 5. Maybe I'll check in chat once. Okay. So if we make incremental updates for linear function approximation of the uh, value function v under policy pi using gradient descent to minimize the squared error between this and bootstrap targets. So these are our targets, and this is our like estimate of that one. Then we will eventually converge to the same solution that we would have if we have used the true vpi values as target instead. So basically, like they are saying that will this, like we are using some estimated minus truth. This is one option. Like you can solve this problem or estimate or value function and basically some bootstrap targets. So are these two equivalent? They are saying, will they land and eventually converge to the same solution? Not necessarily, right? This need not happen. So this is like false. First one is definitely false. For the second one, the basically first, if first one is false, you'll either way like get the answer. But let's see the reason also. Each update moves this our estimate closer to the truth. So eventually the bootstrap targets will converge to the, not necessarily, like this doesn't happen always. So this is also false. Maybe in some case it might happen, but not necessarily it will happen always. Because like our this bootstrap, the biggest issue is like our these targets are also non-stationary, right? Because like there is this component of v here, and this is also changing time step to time step. So this non-stationarity, you remember like that example in which like sir gave in class. So v pi was there, and suppose this is the plane. There is like some mapping. So this was in r is to power n. So n is the number of states, and this is our features. So R is to K feature, suppose we are using, and this is like the projection here. But the thing is like under some mild condition, we will be reaching in some like this distance between them is bounded. And those mild conditions were first linear independence, and second was like on policy. So like it is bounded, but will it exactly match? No. So again, like that makes it false. So if there is no doubt, I'll move to the next one. So again, assertion reason kind of question. So there are a lot of assertion reason today. So to solve the given optimization problem for some states with linear function approximator, in case of discrete space, we need to formulate a classification problem. Do we need to formulate a classification problem here? Like, is it true? Like, we can formulate a regression problem also. Like, this says that we need to formulate a classification problem. Remember, I showed you one setup in which, like, suppose you are having all three actions, suppose discrete number of actions are there, three actions, suppose, and you can have like q values of each of these, and then you can take arguments over these. So we need not formulate it as a classification problem. You can formulate it as a regression problem also. So in case of discrete action space, we need not always formulate as a classification problem. So this is false. Again, like this should give you the answer, but either way, let's see. The given problem is equivalent to solving pi t plus 1 max. Okay. So since they are using linear function approximator, this is fine. But there is one more statement for discrete action space. As we can't maximize it explicitly, we need to formulate. Again, like this statement is wrong. We need not formulate a classification problem. We can formulate a regression problem and then take arguments over it. That is also fine. Classification basically, by classification here, they are meaning you can do this like policy network kind of thing. But we can do in value function based approaches also. We can formulate a regression problem. Now, which of the following is are true about LSTD and LSTDQ algorithm? I think we saw a similar question before also, but some of the options are different here. So this we already saw. Both LSTD and LSTDQ can be used simplistic and not because it has to be on policy. So for the other options, you need to see. Like obviously, both are iterative algorithms where the estimate of the parameters are updated using gradient loss. So were we in this LSTD, were we using some kind of iterative thing? We were instead solving this equation A1, this A matrix is equals to B. This is some kind of, we will give it to some solver. It will solve it for us. Were we doing using this gradient information to of the loss function? No, we weren't using, right? So this is also wrong. So your answer will essentially boil down to either option 3 or D. So both LSTD and LSTDQ are linear function approximation methods. So this, I think, if you have watched the lectures, you can know like essentially non-linear will come from next week. So it has to be linear because we were having those five. So and this also you need to remember linear means linear in parameters, not in features. So features can be nonlinear. This you need to keep in mind, not just in RL, but in general machine learning also. Now the eighth question, again a regression reason. So when minimizing mean square error to approximate the value of states under a given policy pi, it is important that we draw samples on policy. Is it true? Like, yeah, it's true because when minimizing the mean square error, suppose if we are minimizing, remember this is mean square error, not weighted mean square error. So if you are minimizing the mean square error, then you need to draw samples on policy because on policy they will then capture this weight of each state in this mean square error because like the states which are like more important, like they will appear more number of times. So if we do it on policy, then that thing will happen. So this is two. Sampling on policy makes the training data approximately reflect the steady state distribution of the. Okay, so basically this is the point I was making, that if you do it on policy, then essentially like the states will appear approximately in like to be proportional to this steady state distribution. So if we do this on policy, and this will happen. So this is also true. But now you can get the answer by just you need to see whether this is the correct version of this assertion. By that you can get the answer. But both are true. That's the thing. Now we move to ninth question. So tile coding is a method of state aggregation for grid world problems. Consider the following statements. Okay. The number of indicators for each state is equal to the number of tilings. Okay, so yeah, remember this, like we were having these tilings. So one more tiling. So essentially if you consider some state, suppose consider this state, so it will light up like two tilings. So two indicator functions will be needed. So first one is to tile coding cannot be used in continuous state spaces. So suppose if we have, it's not saying like infinite state spaces, but continuous. Suppose we have something like 0, comma 0, 0, comma 1, 1, comma 1, 1, comma 0. This square is there, where like our agent can be at any real point in between. Can we use tile coding over the state space? Yeah, we can use like these tilings can simply like cover this up. So, but it says it cannot be used. So this is false. Tile coding is also a form of course coding. Yeah, like this, if you have watched the lectures, you know, like it is a form of course coding, but like more systematic. Like there are regular squares and everything. A coarse coding is like any shape. So, but tile coding is a type of coarse coding itself, but more systematic in terms of its structure and all. So now I'll move to the last question. So last question says, which of the following are correct values of this matrix in the LSTD method? So remember this is Q, not LSTD. LSTD. So note that the samples are okay. These are the samples. Phi SIAI is the representation for state, and pi is the policy being followed. Okay. So 1 upon L, this phi SIAI. What is the issue in this one? Remember, like it has to be on policy, right? You cannot take this action. You have to take action something like this. Phi SI action. So this is wrong. Now, what is the issue with this one? Oh, okay, so this is using LSTD kind of thing, not LSTD cube. Action needs to be there. 5 of SIA. So this is also wrong. Now, again, like, what is the issue with this one? There's some issue. Yeah, like, again, like that. Pi of SI dash is missing, and one of the parameters should be that, right? So this is essentially a combination of value, and this is also wrong. But 1 by L, this seems to be, yeah, this seems to be the perfect. So yeah, this is the update. This is simple like memory-based question. If you have watched our lectures, you can recall it from that. So now like we have moved to the reading material. So Saturn and Batu, you can read chapter 9. But I think like these LSPI kind of methods aren't mentioned in the book. Maybe I haven't looked at that closely. They might be there in some other chapter. But most of the function approximation topics which are covered in week 8 are in this chapter 9. And you can refer to this least squares policy iteration paper. It's not just for LSPI, but it will provide you summary of LSTD and LSTDQ also. So you can refer to this paper. Again, like one more thing which I wanted to share is this uh, log. This is from OpenAI. So OpenAI you might already know through ChatGPT. So let's go to this link. Okay. Oh, okay, okay. So I'll share this browser again. So this is basically a kind of educational material only from OpenAI spinning up in DeepRL. So this will basically teach you like not just DeepRL, but you can get some now since you are familiar with most of the RL terms. You don't need a deep like very rigorous course from OpenAI in this. So they will like basically review this key concepts in RL, so you can study like this will give you like in one of the lectures someone was asking for notes or something, so you can have your notes from here. So some key concepts, you can have definitions and all, like some refresher of what policies, stochastic policies, parameterized policies, deterministic policies, what all those terms means. You can get in definitions and all from here, sampling also some concepts of other domains also, trajectories, episodes, rollouts. So trajectories are also known as. So this is like basically some briefer reward for this RL terminology, reward and returns, and the RL problem also value function. You can have these different kind of action values on policy, off policy, optimal, Overman equations. So all those like details are here. Some advantage functions. This you'll see later. So this advantage function is basically like how much advantage you get by taking some action compared to the current policies, like value function. So this is the advantage. So this is basically the difference between Q pi of SA minus B pi of S. So maybe like this basically means that A is better than the action which is recommended by policy. So if the policy recommends some action A dash, and if this advantage is positive, then this like action will be better, and some other formalism. So this is like some kind of brief also. So it will provide you some concepts and kind of RL algorithms also. So this is like some basic terminology of RL, like taxonomy of RL algorithms, which is like this is basically a division. Like there could be model-free algorithms, model-based RL, policy optimization, Q learning. So basically, like whatever you see here, you might realize that you are not seeing algorithms which have been covered in RL, because like these are mostly our deep RL kind of algorithms. So eventually, like next week, you will see DQN, and like these algorithms are slightly more complicated. There are actor critic algorithms which combine value based approaches and policy based approaches. So model free RL. So Q learning is essentially value based method, and this is like policy based methods. And all like both of these come in model free RL. So there are policy based methods also. I think in week 9 you will see those policy based method, and there are methods which will combine value like which will combine concepts of value based methods also and policy based methods, and those are known as actor graded methods. So in actor is basically policy based concepts, because actor like policy basically determines how you act in the environment. It's a mapping from state to action, right? So it will determine how you act in the environment. So that component is called actor, and critic is basically it will provide some value. So for each state or each state action where you are given a value or action value, so basically value like you can say V and Q value. So all those values like they kind of provide some criticism, like how good this state or state action pair is. So like those are like basically called as critic methods. So sometimes like some literature says like these policy-based methods as actor methods and this value-based methods as critic methods. And there are approaches which will combine both these actor and critic. So those are known as actor critic methods. And then there are more sophisticated techniques like proximal policy optimization, trust region policy optimization. And then there is this TD3. This TD doesn't stand for temporal difference. It's an advancement of DDPG. Its full form is something else. So basically, like you can see all those algorithms also. I'll show you. So deep Q network is there. Then this is hindsight experience. We play all those algorithms. Alpha zero comes here. Like you need to have a model. So this is like non-exhaustive. Like there might be some algorithms which might not be here. Some more might have come up later. So all those algorithms are there. Then you can like learn the difference between model free and model based. Okay, so you can learn. So all these like details are there. You simply have to read. So this is the like links of algorithms, each of these algorithms. So I was mentioning this TD3. It's not like temporal difference, but it's twin delayed DDPG. So you can like simply go to each of these algorithms and maybe like I'll show you. So these are like this is the links to each original paper of that. Like these people like proposed this method. So it came in 2016, essentially after like our lectures were recorded. So most of these algorithms came up after those lectures were recorded. So you can like see these like algorithms. So basically like this is one of the resource like you can use other resources also for DeepRL, but this is from OpenAI, so you can trust it. So that is what I wanted to say. And then like they will provide, since like I mentioned to you some of the limitations of value function based approaches, like so these guys like have a special focus on policy based methods. So you can have like much details about policy based methods. So I think in our lectures like policy based methods are devoted only one lecture. Like week 9 like will cover basically the meaning of value function based methods, then maybe a video or two on policy based methods, and then eventually we will move to actor critic. Then from week 10 like we move to advanced RL, and which will be hierarchical RL and then bomb DPs and all. So essentially like week 9 will be end of like main concepts of RL, then we'll move into advanced concepts. So if you, so basically what I'm trying to say is deep RL isn't covered in this um um discourse. So basically like if you like there might be some other course on deep reinforcement learning you can find, but like this is a good blog you can read. Maybe if I find something like I'll share with you in the next week. Okay, so that was it about this. So this link is already there in the slide. I'll share the slide again. So you can simply click this link and go to that website. Okay, so that was it from my side today. So thank you.
Sir, what is
Yeah.
that wording? Is spinning up? Spinning up means what, sir? Spinning up.
It's just a name, just a fancy name. Nothing much. And don't think much about it. Just
Okay,
some
okay.
fancy. Yeah.
Sir, future research topics kind of things can you share in future of your videos lectures, sir? Uh, like
Future.
current research
So
topics in deep
yeah,
oral
yeah.
or oral, whatever.
So you remember like in one of the lecture I shared those like one RL conference happened at IISc. So you can find research
Ah,
topics
yes,
like
sir.
what.
Yes, sir. I
Yes.
remember.
And you can go to this RL summer school. There also like there are some lectures like which are mostly related to new topics. So all those new topics. So most of the research is going in deep RL as of now. So you can read up like these papers which have been linked by OpenAI spinning up. So you can read those papers and from there like you can gradually move forward in what is happening in the current world. So you can
Thank you so
refer
much,
to
sir.
IASC ones also and RL summer school also. Yeah.
Thanks a lot, sir. Great
Yeah, yeah.
session, sir.
Okay. Welcome. Okay. Okay, so then like I think that's it from me in this session. Okay, so see you next Tuesday. Okay, now I'll like stop recording. Stop sharing first.